Continuing on with homework 19 then, now we're back to all those hypothesis testing like we were doing last week. We did 3 different kinds of hypothesis testing. Last week we did the hypothesis test for the population mean. Now we're doing the hypothesis test for the difference of the population mean, but it's going to look really similar to what we did last week. So, number 1 says, according to the historical data, the life expectancy in the United States is equal to the life expectancy in Japan. A new study has been made to see whether this has changed. Records of 240 individuals from the United States who died recently are selected at random. The 240 individuals lived an average of 76.8 years with a standard deviation of 5.4 years. Records of 270 individuals from Japan who died recently are selected at random and independently. The 270 individuals lived an average of 77.4 years with a standard deviation of 5.3 years. Assuming that the population standard deviation of the life expectancy can be estimated by the sample standard deviations, since the samples that are used to compute them are quite large, at a 0.1 level of significance, is there enough evidence to support the claim that the life expectancy U sub 1 in the United States is not equal to the life expectancy U sub 2? So, I'm going to move this up just a hair so we get the whole table in here. There we go. My null hypothesis. Whenever we did the null had the equal, right? So in this case, we're going to have U sub 1 equals U sub 2. Are the two things equal? For my alternative hypothesis then, we're going to have the not equal. U sub 1 does not equal U sub 2. On these ones, we know what the type of the test statistic is because it says it up here. But it is going to be the z-test. So, our formula that we're going to use looks like this. X bar sub 1 minus X bar sub 2. The differences between my two means. Technically, it's minus U bar sub 1 and U bar sub 2, but this value is always going to be 0 if those two things are equal. So really when we do our formula, we don't even have to worry about the second part because if I minus 0, it's just going to stay that. So you'll see that if you look in the book on the formula that they do write that in there, but it's 0 and so you can ignore it. On the bottom of my fraction, I'm going to have the square root of the population standard deviation squared sub 1 over n sub 1 plus the population standard deviation squared sub 2 over n sub 2. So we do this z-test because we have the population standard deviation as opposed to the sample standard deviation. So looking back at my word problem, according to my historical data for the first one, records of 240 individuals. So N1, 240 individuals. The average, so X bar 1, is going to be 76.8 years. My standard deviation, so sigma sub 1, my standard deviation, is 5.3 years. For the second survey, we did 270. So n sub 2 is going to be 270. My average of those people was 77.4, so X bar sub 2 is 77.4. My standard deviation was 5, whoops, I did that again. This top one was supposed to be 5.4. There's my top one. When you jump back and forth, it's hard to read. That should have been a 5.4 for my standard deviation for the first one. 76.8 years with a standard deviation of 5.4. On the second one, it's the 5.3. So sigma sub 2 is my 5.3. All right, so plugging those into my formula. I am going to do 240 minus 270. That's going to be on top my fraction. I can ignore this end part because I know it's going to be 0. Over the square root of 76.8 squared over 240 plus 77.4 squared over 270.
Isn't the top part supposed to be the 76.8?
I'm glad you're paying attention. I use the ends instead of the means. Okay, how about I use the mean? 76.8. Man, and then I didn't even use the standard deviation. Let me just start that all over. Gosh darn it. Okay, so on the top, we have the mean of 1 and the mean of 2. So 76.8 minus the mean of 2 is 77.4. On the bottom, we have the standard deviation. There it is, 5.4 squared over 240 plus my standard deviation here was 5.3 squared over 270. There, that probably looks better. So 76.8 minus 77.4 over the square root of 5.4 squared over 240 plus 5.3 squared over 270. We are rounding this to 3 decimal places, it says, for the value of our test statistic. Negative 1.263 is the value of my test statistic. Now, if you remember from last time, we had 2 different things. They either ask you for the p-value, which is your percentage, or your critical value. When they do the critical value, you're doing z sub something. If they ask you for the p-value, use p is greater than whatever that number is. So in this case, first of all, I have to figure out on here, I am doing a 2-tailed test because I have an equal and a not equal. The 1-tailed test, we had the greater than and the less than. So it's a 2-tailed test, and since this is a 2-tailed test, we have to take alpha divided by 2. So 0.1 divided by 2 would give me 0.05, which means this side is 0.05, this side is 0.05. So when we find our critical value, we're going to do z sub 0.05. And again, when we get that number, we have both the positive and the negative because we're on both ends of our normal standard curve there. And so you're just going to use the Alex calculator and do the z sub 0.05. And this is going to be 3 decimal places again. 1.645. So 1.645 would be my bigger end, negative 1.645 would be my other end. So this is the negative 1.645. This would be the positive 1.645. Okay? So when it's a 2-tailed test, I have to divide that by 2. If it was a 1-tailed test, I just leave it alone and use whatever the number was there. Now, if you remember again from our hypothesis testing before, this section is the null section that's in the middle. The 2 sections on the end are your alternative sections. We have to figure out where we land. So we're looking at our test value, the negative 1.263 and trying to figure out what section does it end in, or does it end up in. Is it less than negative 1.645? Is it between negative 1.645 and positive 1.645? Or is it bigger than positive 1.645? Well, if I have a negative 1.263, where would that end up? Since it's negative, is it less than that or bigger than that? Negative 1.263 is. It is? If I have a negative 1.263, is it less than negative 1.645? It'd be bigger than that, right?
Yeah. Oh, I thought you meant the point.
So I'm comparing this number to these numbers.
Oh.
So if I were putting this in order, that negative 1.263 would be between the negative 1.645 and the positive 1.645, right? Since I'm in the middle section, I am going to accept that the null is true. So this is my true statement. This is the one that is not true, right? So the question says, can we support the claim that the life expectancy in the United States is not equal to the life expectancy in Japan? Can we accept that they're not equal? No. We're saying they are equal based on our test, right? They are equal, so we can't say they're not equal. We're going to say no. All right. Number 2 then here. Number 2. Now this is one where they give us...
18?
We are in 19. We finished 18 already. Right? We got partway through 18 last time, so we've already finished that. Now we're on to 19. So number 2 and number 19 is where we're at. So, it says, a random selection of volunteers at a research institute have been exposed to a typical cold virus. After they started to have cold symptoms, 20 of them were given multivitamin tablets daily, which contain 1 gram of vitamin C and various other vitamins and minerals. The remaining 20 volunteers were given tablets only containing 4 grams of vitamin C for each individual. The length of time taken to recover from cold is recorded. At the end of the experiment, the following data are obtained. So if they had the multivitamin, these are the number of days it took them to recover. If they had just vitamin C, here's my list of number of days. It is known that the population standard deviation recovery time from my cold is 1.8 days when treated with the multivitamin. And the population standard deviation for recovering from my cold is 1.5 days when treated with vitamin C. It is also known that both populations are approximately normally distributed. The research claimed that the mean recovery of U1 of the patients treated with multivitamin is less than or equal to the mean recovery time of U2. At a 0.01 level of significance, is there enough evidence to reject this claim? So, in this case, the question says that is it less than or equal to, right? The equal to always has to go with the null, so that's my null hypothesis. Is the mean of 1 less than or equal to the mean of 2? Which means my alternative hypothesis would be, is the mean of 1 greater than the mean of 2? So the null always has the equal whichever way it works out, but this one said less than or equal to, so it has that in there. Again, we are going to do the z-test since they've given us the population standard deviation.
Can you print me 19, please?
After I do this one, because otherwise I have to erase everything and start over. Okay, so on this one, first thing we need to do is find the means of our data. They gave us the list. You can either add them all up and divide by 20, or you could use your calculator, put them into list 1, and do the one variable statistics. We really don't need any of the other statistics from the one variable statistics, so it's probably just as easy just adding all of these together, add, and divide by 20, since there's 20 numbers on the list. So just to make this go a little quicker, Fidelity and Leanne, you want to add the bottom ones, and you two can add the top ones since I see you're already punching into your calculator. And just find the total.
I use this calculator?
Yep, just use your regular calculator. Just add up that bottom list of numbers. I want to find the mean or the average, so I'm going to add them all together and divide by 20.
Can you clear out my thing? I don't know what's going on here.
If you hit second function and quit. Okay, we're just going to type them in here. We're not going to put them in the list. You could put them in the list, but it probably isn't really necessary.
The first one?
So you're going to do the bottom one. So do the bottom list, the 4.3 plus the 4.0 plus the 4.9. Add all those numbers up. Those two already started, so I just let them do the top. So once you get your numbers, let me know what your sum is from adding all those together. That's what I got. So on the top one we get 116.4. Gotta get the bottom one added up yet here. They started later. 96.7. So for X bar 1, we're going to take the 116.4, which was the total of these numbers, divided by 20, since there's 20 numbers on your list. So if you take 116.4 divided by 20, you get
5.82.
What was that?
5.82.
5.82. Then we're going to do our X bar for our second list. On our second list, the sum of all those numbers was 96.7. Again, there's 20 numbers on our list. So if we take our 96.7 divided by our 20, .835. So this was our 5.82. This was our 4.835. So to find the mean, we just add them up and divide by how many numbers are on our list. All right, the standard deviations they gave you. The population standard deviation time when treated with a multivitamin was 1.8. So that is going to be 1.8 for our sigma sub 1. Standard deviation for the second one was the standard deviation for vitamin C, which is our 1.5. They were nice and gave us those numbers, so we didn't have to figure those ones out. N1, it's going to be 20. We had 20 numbers on our list. N2 is also going to be 20. We had 20 numbers on our list, right? So now we have to go back to that formula that we did, and I wrote down on the previous page that said we're taking X bar 1 minus X bar 2 divided by the square root of my standard deviation squared 1 divided by N1 plus my standard deviation squared 2 divided by my N2. So plugging those numbers in from our data then. 5.82 minus 4.835. Divided by my square root of 1.8 squared over 20 plus 1.5 squared over 20. That is going to give us that test value. I got to move my screen up a little higher, but we'll know that bottom one's a yes or a no. And again, that one you could put in your Alex calculator. If you wanted to try to put it in the regular calculator, you could also do that. But the Alex calculator is probably just as easy to use. .880 they're going to say. 1.880 is what you should get when you do that calculation. So this time we're going to do the p-value. You have to remember here we are doing a one-tailed test. And when we do our one-tailed test, we are looking at what the alternative one is. And so we're looking at for the greater. We're doing the p-value, and on your Alex calculator, when you do the p-value, you have p of z is, and what's the symbol there? It's a less than. So remember that when we had the less than, but we were really figuring out the greater than, we had to do 1 minus the p of z is less than, right? Because we want to check the greater than, that's our alternative hypothesis. We're going to do 1 minus p of z is less than our 1.880. Okay? So if this is a right-tailed test, I got to do the 1 minus. If it was the left-tailed test, then I wouldn't need the 1 minus because I'd be checking the other direction. And so when we go ahead and put that into the Alex calculator, 1 minus p of z is less than our 1.880, we get what? 0.30. Okay. When we test the p-value, we're testing the percent against the percent here, which is the 0.01 level of significance. So, when our test value is less than the level of significance, we rejected the null. When the test value was greater than the level of significance, we accepted the null. Remember that from last week, vaguely? So in this case, my value here is 0.030. I'm comparing it to 0.01. Is 0.03 less than or greater than 0.01? It is greater than. Since my test value is greater than my level of significance, I'm saying that I have a 30% chance compared to 10%. It means I am going to accept whatever the null statement is. So that means this is the true statement. This one is not true, right? The bottom got cut off, but you can read it on your paper. Can we reject the researchers' claim that the mean recovery time when treated with a multivitamin is less than or equal to the mean recovery time when treated with the vitamin C only? Can we reject the claim that it is less than or equal to? Can we reject this? No, that's the true statement, right? This one was the not true, so this is the one we're rejecting. We're rejecting that it's greater than. We're accepting that it is less than or equal to. So can we reject that claim? No. No, we cannot. So can we reject this one? Nope, we're accepting that that is true. The other one was the not true statement. All right, number 3. That time I got the whole thing on there. It said, oops, I got to print. Leanne didn't yell at me and say, hey, you're supposed to print that for me. Print. It's warming up, I can hear it. All right, while she's grabbing that, I'll start reading this since it's long. It says, a study conducted by the research department of a pharmaceutical company claims that the annual spending per person for prescription drugs for allergy relief, use of one, is greater than or equal to the annual spending per person for a non-prescription allergy relief medicine, U2. The health insurance company conducted an independent study and collected from a random sample 270 individuals for prescription allergy relief medicine. So N1, 270 people. The sample mean was found to be 17.7 with a sample standard deviation of $5.6 per year. So X bar 1 is 17.7. Sigma 1, my standard deviation, was 5.6. They also collected data for non-prescription allergy relief medicine. An independent random sample of 225 individuals, so N2 is 225, yielded a sample mean of $18.3 per year and a sample standard deviation of $4.1 per year. So X bar 2 is my 18.3, sigma 2 is going to be 4.1. Since the sample size is quite large, it is assumed that the population standard deviation of the sales per person for prescription and non-prescription allergy relief medicine can be estimated by using the sample standard deviation values given above. Is there significant evidence to reject the claim made by the research department of the company at a 0.5 level of significance? Well, their claim was U1 is greater than or equal to, since that has the equal to, it's going to go in for our null, our U2, right? That was the claim. Claim is it's greater than or equal to, the null always contains the equal to, which means my alternative hypothesis would be U1 is less than U2. So when I'm doing my one-tailed test, this time I'm doing a less than value over here. Type of test statistic, again, we're going to do the X, or the Z test. And we have to find the value of our test statistic. So when we're finding the value of our test statistic, we're going to take X bar 1 minus X bar 2. So 17.7 minus 18.3 over the square root of the standard deviation from the first one squared. So 5.6 squared over the number from the first one, 270, plus the standard deviation of the second one, 4.1 squared, over the number from the second, 225. That's going to give us the value of our test statistic, rounding to 3 decimal places.
Can you type it in this calculator?
You can, but
Because I can't use the Alex right now.
just switch to a different question. It'll still remember you knew that one. Now you can. Otherwise, you've got to put probably a bunch of parentheses and stuff in there. So it's easier probably just put it on the
How do
Alex
I
one.
switch to a different question?
Just go on the drop down on the top here, or go continue on my path first of all. And you just need to find one where the calculator is active.
Yeah, keeps going back to
On the
the
slope,
square.
it's probably not. So click that drop down and just pick a different one. Like, let's see if that one gives us the calculator. Nope. Oh, that one's locked. How about that one? Yep, that one the calculator's active on. So we can use the calculator there. All right. So the value of our test statistic to 3 decimal places is
-1.373.
-1.373, which is a good sign that it was negative because it's on this end, right? We're doing a left-tailed test on this one. So on this one, when we're finding our p-value, since we're doing the p-value, we're doing the p is, p of z is less than. So on this one, notice we don't have to do the 1 minus because we are doing the less than, right? P of z is less than, does it have the equal to sign underneath? Or is it just a plain less than?
Less than or equal.
Okay, less than or equal to -1.373. So we're just doing that calculation. Since we're going to the left, we don't need the 1 minus like we did when we had the right-tailed test on the previous one. So the value of our p-value, the p-value is the percentage of stuff that's in that section. That's what the p-value stands for. To 3 decimal places, when you do p of z is less than or equal to -1.373. 0.085. So when we do the p-value here, we're comparing it to the level of significance, right? So is 0.085 less than or greater than 0.05? 0.085 compared to the level of significance of 0.05.
That's greater.
It is greater than. And if this is greater than, we are going to do what with our null? Except that the null is true. Except the null. So this is our true statement, that we are greater than or equal to. The not true statement is that we are less than. So now our weird question. I hate it when they say reject instead of accept, but they did that a lot. Can we reject the claim that the annual spending for prescription drugs is greater than or equal to the annual spending for non-prescription allergy relief? Can we reject this claim? No, that's the true statement. We're not going to reject that. It's true. So our answer here, can we reject that claim? No, we can't. We're saying that's the true statement.
I'm finally getting it.
Well, by the time we do 4 more of these, you'll get it, hopefully.
I got it. It's just the end part.
The end part is tricky.
Yeah, the end part really.
The end part is tricky. This whole page is all hypothesis testing using different tests, so we'll get a whole bunch more practice. It took me a while when I was working through all this last fall to figure it all out too. All right. This one we're doing the hypothesis test for the difference of population means, a paired comparison. So it says here a personal computer manufacturer is interested in comparing assembly times for 2 keyboard assembly processes. Assembly times can vary considerably from worker to worker, and the company decides to eliminate this effect by selecting a random sample of 8 workers and timing each worker on each assembly process. Half the workers are chosen at random to be used for process 1 first, the rest process 2 first. Each worker in each process, the assembly time in minutes is recorded as shown in table 1. So for worker 1, process 1 took 33 minutes, process 2 took 30 minutes. The difference between process 1 and 2 was 3 minutes, and they filled out the table. Based on these data, can we conclude at a 0.5 level of significance that the mean assembly times for the two processes differ? Answer this question by performing a hypothesis test regarding U sub D, which is the difference, the population mean difference in assembly times for the two processes. Assuming that this population of differences, process 1 minus process 2, is normally distributed. So here for my null, I'm going to use U sub D. For the null, we always have the equal. So I'm going to say that the difference is equal to 0 if there's really no difference, right? There's no difference, the difference would be equal to 0. If there is a difference, it is not equal to 0. On this one, we are going to do the t-test when we compare these two things. And when we do the t-test, we have to have our degree of freedom. Our degree of freedom, again, is n minus 1. How many people did they survey? How many workers do they have? 8. So n is equal to 8, so n minus 1, going to be 7 for the degree of freedom, right? On our t-test, the degree of freedom is always n minus 1. So, we are going to then use this crazy formula again for our test statistic. For our test statistic, we are going to do what they call d bar minus u sub d, which again in this case is always going to be 0, just like on that other one. The difference is going to be 0 if there are no difference. So we really don't have to do much calculating there. And then we're going to have S sub d for our standard deviation over the square root of n. So first thing we need to know is, what in the heck is d bar? D bar is the mean of your differences. So like on that previous one where they gave us that table, we have to find the average of the differences. So we've got to add up the values in this column and then divide by 8. So add them up first, and then it's going to be divided by 8 since there's 8 numbers there. So you're going to do 3 plus 10 plus 0 plus 15 plus negative 11 plus 11 plus 8 plus 21 and find that sum up there on the top. $57 yet? For some reason I didn't write it down, but 57 divided by 8 then is going to be what the mean of our differences are. If you take 57 divided by 8, what do you get?
7.125.
Okay, that's the right number. 7.125. All right. Did I use my calculator on this one? I'm trying to see if they gave me a standard deviation. No, I did use the calculation. This is the standard deviation of my differences. On this problem, they didn't just give it to me. So I either have to use that great big long formula for standard deviation or use our statistics on our calculator. We could have found the mean a little, since we have to do both of them. We probably should have just used our calculator for both of them. So let's just go ahead and grab our calculator. Under the stats in list 1, we're going to enter in this data because we probably don't want to have to do the standard deviation formula since it's that great big long formula. So stat 1 to edit, put in those values from the table. That'll just make it a little easier. 3, 10.
Or the differences?
The differences, yep, of the differences, that's the one we're doing. So do your differences in list 1. So, stat 1 to edit, put it in L1,
What does it sort it?
and then you don't need to sort it because we're just going to do the calculation. You could if you wanted to, but we're just going to do stat and calculate. Remember doing that, going over to calc, and then doing 1 to do our one variable statistics. And we want to do the one variable statistics on list 1. Your mean, which is your X bar on your calculator, should be the 7.125. We already figured out doing the long way, doing it the manual way. Standard deviation, if you look on there, you want the one with the S. What do you get for your value for your standard deviation?
For the X?
Yep.
I don't know if that's right. Did I do that right?
9.8, let's see, yep, 9.819. Yep, that looks like it's the right one. So see the S there, S sub X on that, on a calculator? So you should get 9.891. 9.819.
Bar?
Variable. Yep, one variable statistic you have to do. 1.819. Got it down the right way. 9.819. So you do your one variable statistics on list 1 like we did hopefully a bunch of times by now. Alright, that way we don't have to use the formula for standard deviation. The mean formula isn't easy enough to do, but when they don't give you the standard deviation, that's a pain, and that formula is. So now that we know those numbers, we are going to do the 7.125 divided by the 9.819 over the square root of n. N was 8. There were 8 people that they were comparing. And again, when you figure out that answer, you're going to round to 3 decimal places. Yep. 2.052 is what you should be coming up with. So that's the value of our test statistic. We are going to do the critical value. When we do the critical value, that's always when we have the variable subscript. So in this case, since we're doing the t-test, we're going to do t sub something. Now in this case again, since we have an equal and a not equal, what we're doing that two-tailed test, right? And so we have to divide that by 2. If it's a one-tailed test, we'd use that number, but since it's a two-tailed test, I'm going to take my 0.05 and divide it by 2. And so if I do that, I'm going to get 0.025, right? So t sub 0.025 with a degree of freedom of 7. So whenever it's an equal and a not equal, it's a two-tailed test. We're going to divide that by 2 because we're figuring out each end separately. If I punch that into the Alex calculator, t sub 0.025 with the degree of freedom of 7, we get what number? 2.365, which means this side is negative 2.365. It's going to be between those two numbers. So negative 2.365 and positive 2.365 are going to be our critical values. When we do the critical value, the null is in the middle, the alternative ones are on the end. We are checking in which one of those 3 sections does positive 2.052 fall. Is it on either end or is it in the middle of those two numbers? It's in the middle, right? So 2.052 would fall between those two quick critical values. That means we're in the section where we're going to accept the null. The null is the true statement. That means the other one is not true. And so our question says, at the 0.5 level, can the company conclude that the mean assembly times for the two processes differ? Can we say they differ? No, we can't say they differ because we're saying they are the same. They're equal, right? They're either equal or they differ. We're saying the differ is not true, so no, we can't say that they differ. We're saying they're the same. We're saying they're equal. So, number 5, can I get the bottom in there? Kind of. I'm just going to set it right there and read off my paper. Number 5, same thing. We are just going to use our calculator to do the mean and the standard deviation because on these ones they're not going to give them to you. So in list 1 you can start typing that in if you'd like. It says a personal computer manufacturer is interested in comparing the assembly times for the two keyboard assembly processes. Process 1 is the standard process used for several years. Process 2 is an updated process, hoped to bring a decrease in assembly time. Assembly times can vary considerably from worker to worker, and the company decides to eliminate this effect by selecting a random sample of 12 workers and times on each worker for the assembly process. Half the workers are chosen at random to do process 1 first, the rest do process 2 first. For each worker, each process, the assembly time in minutes is recorded in Table 1. Based on the data, can the company conclude at a 0.10 level of significance that the mean assembly time for process 1 exceeds that of process 2? So, this one wants to know if process 1 exceeds process 2 instead of saying the difference. If something exceeds something, it means that it's greater than, right? The word exceeds means greater than. Since this is a greater than, that's going to be my alternative hypothesis because my null always has to have the equal. So here, U sub D either is going to be, in this case I'm going to do the bottom one first, the greater than 0. It exceeds it, which means my other one, my D is kind of big on those. It's supposed to be a subscript. My other one then, for my null, since this is a greater than, would be less than or equal to, because the null always has to have the equal to one, right? So if it exceeds, I'm doing greater than 0. If it doesn't exceed, the difference is less than or equal to 0. So in order to do our formula, we have to find the mean of the differences and the standard deviation of the differences. And so in your calculator, in list 1, if you haven't already, put all those numbers into list 1. And then we're going to calculate the one variable statistics. So your mean, again, is just going to be the x bar. Your standard deviation is going to be the s of x on your calculator.
The 12.104.
For which one?
The S.
The standard deviation, 12.104. The mean, again, we can just use it off the calculator instead of figuring it out the long way like we did last time. The x bar is?
X bar is 2.167.
Whoops, 167. 2.167. Yep. If you really wanted to, you could add all those up and divide by 12 and you should get the same number, but since we're doing our standard deviation, we could just as well use the calculator for the other number. All right, so our formula then, when we did our formula, we did the 2.167, how come I don't want to write the 1 today? 2.167, which is the mean of our differences. over the 12.104, which is the standard deviation of our differences, divided by the square root of n. In this case, n is 12. We had 12 workers or 12 people in our table, right? Oops, I forgot to do my test. We'll put that in there after we do the value of our test statistic. We'll just go out of order. So when we divide that out, 2.167 divided by 12.104 divided by the square root of 12. 0.6, whoops. Now I'm writing the answer in the wrong spot. 0.620. I skipped over the type of test statistic. The type of test statistic that we're doing on this one is our t-test, right? With a degree of freedom of, what is going to be the degree of freedom? 11. N minus 1, the degree of freedom, so 12 minus 1 is 11. We need to know that in order to calculate our critical value. On our critical value here, this time we are doing, does it exceed, is it greater than? We're just doing a one-tailed test and not a two-tailed test. So when we do our critical value, we don't have to divide by 2. We're just going to use the 10% level of significance. So we're going to do t sub 0.10 with a degree of freedom of 11. And so on our calculator, when we put that one in, we get 1.363. 1.363. So 1.363 is our dividing part. 1.363. The greater than is my H1, my null. The less than or equal to would be on the other side then, right? Since my difference is greater than 0 is my alternative hypothesis. So now what I'm checking is, does my test value fall on the left side or on the right side of that critical value? On the left side. It's in this section right here, right? It's smaller. That's my 0.620. That was my test value, which means since it falls on the left side, I'm going to accept that the null is true. This is my true statement. This one is not true. So, at a 0.1 level, can the company conclude that the mean assembly time for process 1 exceeds that of process 2? The exceed was the greater than. Can we say that's true? No, we can't, right? That was the not true statement. Can we say that it's true? No. I don't know why that has a yes, yes, and a no, no, but no, we can't say that's true. That was our not true statement, the greater than. Number 6. Again, if you want to get typing those in so that we can do our statistics, go ahead and put those in list 1. It says the owner of a chain of mini markets wants to compare the sales performances of 2 of her stores, store 1 and store 2. Sales can vary considerably depending on the day of the week and the season of the year, so she decides to eliminate such effects by making sure to record each store's sales on the same sample of days. After choosing a random sample of 12 days, she records the sales in dollars for each of the stores and the days shown in the table. Based on these data, can the owner conclude at a 0.5 level of significance that the mean daily sales of the two stores differ. So this is like problem number 4 was, where they differed, right? So if they differ, we're going to say either my U sub D is equal to 0 or U sub D is not equal to 0. So here we're doing one of those two-tailed tests. Either it's in the middle or it's on the two ends, right? Type of test statistic. We know we're doing the t-test. We have to have our degree of freedom. What is our degree of freedom going to be? 11. The degree of freedom is always n minus 1. N is 12 days. So degree of freedom is going to be 12 minus 1, which is 11. Now we can compute the value of our test statistic after we find our statistics here. So we need the mean of the difference and the standard deviation of the difference by doing our one variable statistics on that list of data. So in your calculator, in list 1, if you have all that data in, then stat, calculate one variable statistics so that we have our numbers that we need for the problem. So we're putting in all these numbers here from the difference column. So we hit stat 1, and then we put our list in list 1, and then we do stat and go over and calculate to do the one variable statistics.
So did I do this right?
What did we get? Oops, wait a minute. That doesn't look like we got the right numbers there. Let's go back to your list. Hit stat 1 for me. All right, we got 150, negative 48, 143, 231, 146, 236, negative 72, 7, 244, 321, 75, and we should have a 60 on the end. Oh, we missed the 60. Enter that in. Now let's try it. So stat, go over to calculate, and 1 for one variable statistics, or just enter. And enter through that. There, that looks better. Just forgot the bottom number. You maybe didn't hit enter on it.
Yeah.
All right, so we get 124 point, I don't know why I carried that out so far. Does it tell me 3? So I'm going to do 147 then to go to 3 decimal places, right?
Is it, did I do?
Whoops. Man, I just keep switching numbers today. 124.417. How about that? That look better?
Yeah.
Okay. And for my standard deviation, we would have
123.180.
Yep. So the standard on here, your mean is the x bar, your standard deviation is the s of x. That's your sample standard deviation. All right, we now can throw those into the formula. So in the formula, we have d bar on the top over s sub d divided by the square root of n. So we're going to have our 124.417 divided by our 123.180 over the square root of 12. 12 was the number in our sample, right?
$3.499.
3.499. 3.499 is the value of our test statistic. We need to find our critical value. when we do the critical value, that's the T sub, right? Since we're doing a two-tailed test, we have to divide our significant level of significance by 2, right? 0.05 divided by 2 would give me 0.025. So we're going to do T sub 0.025 with a degree of freedom of 11. Whenever we have the two-tailed test, we're going to divide that by 2.
2.201.
So this side is 2.201. This side would be negative 2.201. So negative 2.201 to positive 2.201. And then, of course, the last part, at the 0.5 level, can the owner conclude that the mean daily sales of the two stores differ? So we want to figure out our test value. Where does our test value fall? If it's in the middle, we're going to accept the null. If it's on one of the two ends, we're going to accept the alternative. Where would 3.499 fall?
On the right.
On the way in section over here, right? 3.499. That means that the null, or that we're going to accept the alternative hypothesis that the null is the one that's not true. So this one's not true. This one is our true statement. Can we conclude that they differ?
Yeah.
Yes, they do differ. They're not equal. So yes, we're saying the not equal is true. So yes, they do differ. Number 7, again, we're doing a hypothesis test for the difference population mean. We're going to do the t-test on this one again, if I could get this to stop where I wanted it to. And so, it says the University Data Center has 2 main computers. The center wants to examine whether computer 1 is receiving tasks which require comparable processing times to those of computer 2. A random sample of 15 processing times from computer 1. So n is going to be 15. Show a mean of 38 seconds. So x bar is 38 seconds with a standard deviation of 15 seconds. So my standard deviation, S1, is going to be 15. I should put ones there since we have 2 different things we're surveying. Then we're going to do computer 2. So a random sample of 10 processing times from computer 2. N2 is going to be 10. Show a mean of 51 seconds. So x bar 2 is 51 with a standard deviation of 19. S2 is 19. Assume that the populations of processing times are normally distributed for each of the 2 computers and that the variances are equal. Can we conclude that at a 0.1 levels of significance that the mean processing time of computer 1 is less than the mean processing time of computer 2? So if I'm going to say that U1 is less than U2, would that be my null or my alternative hypothesis? That's my alternative one, right? Now they're going to do something weird on this because they like to compare it to 0 like we were doing on the previous problem. So what they're going to end up doing is taking this and moving it over here. So they're going to say the mean of 1 minus the mean of 2 is less than 0. Here then, the mean of 1 minus the mean of 2 would be greater than or equal to 0. All right, so now this is going back to the formula that we started with way back on homework 18, where we first have to find our SP number. The SP number again was N1 minus 1 times S1 squared plus N2 minus 1 times S2 squared over my degree of freedom. My degree of freedom, again, when we did our degree of freedom, was the N1 plus the N2 minus 2. This was from homework 18, problem 6, 7, and 8, or somewhere in there. That's the first part of our formula. So when I find SP, N1 is 15. So I'm going to have 15 minus 1 times my standard deviation squared. So my standard deviation is 15, so 15 squared. I got too many 15s in this problem. Plus N2 was 10. So 10 minus 1 times my standard deviation is 19. So 19 squared, if I sneak that in behind there. And then my degree of freedom is going to be N1 plus N2, so 15 plus 10 minus 2. That would be 25 minus 2, which I'm just going to go ahead and calculate as 23 then, right? So first thing we have to do is figure out what SP is. We are going to carry that out to 3 decimal places. Intermediate calculations to 3 decimal places.
What's that say right there? 19
Squared.
squared.
That was my S2 squared that I didn't have room to write, so I tried to smush it in there. So, yes, that was 19 squared. So if you figure out that number, what do we get? And if you wanted to make this so you could type it in faster, you could just do this calculation and do 14 times 15 squared and 9 times 19 squared divided by your 23. And then you don't have to put all the parentheses and stuff in there, right? What did we get when we figured out that value? $278.217. Okay, so same formula we used on homework 18. Now we have to figure out the test statistic, which I skipped over that. We better put that in there. We're doing a t-test with a degree of freedom of 23. That was the bottom number here. So now for my formula, I'm going to do the mean of the first one minus the mean of the second one over, and then I'm going to have the square root of the SP times 1 over N1 plus 1 over N2. So it looks like a lot like the confidence interval formula, except for you're dividing instead of subtracting. So, mean of the first one would be 38, minus the mean of the second one, which was 51, over the square root of the number we got over here, 278.217, times 1 over N1, which is 15, plus 1 over N2, which is 10. Again, all that goes under the square root when you type that in. So make sure as you go to the next part, you click right behind whatever you have there. again, we're going to round this to 3 decimal places. Negative 1.909. Okay. So on this one here, when we think about our test, we are doing just the one-tailed test. Since the alternative hypothesis is a less than, we're doing the less than. When we do the critical value, we would end up getting the positive number, which would be the right-tailed test. So when we do it, we're going to use negative the value. So you're going to do T sub 0.1 with the degree of freedom of 23, but instead of using the positive answer, you're going to use the negative answer because you're doing a left-tailed test instead of a right-tailed test. Right? Just like when we do our one with the 2 sides, we have both a plus and a minus. We want the minus end of our graph. So if you do your degree or your T sub 0.1 level of significance, since it's just a one-tailed test with a degree of freedom of 23, you get 1.319. Since we know we're on the left end, we're going to use negative 1.319. Okay? We then are going to test that out. So again, this section with the less than is our alternative hypothesis. The other side would be our null hypothesis. We're trying to figure out in which side does negative 1.909 fall. Is it on the left or is it on the right of that critical value? It's on the left side, right? This is smaller than this is. So my negative 1.909 would fall in that section there on the left side. That means that my alternative hypothesis is the true one, the null is the one that's not true. So, can we conclude that the mean processing time of computer 1 is less than the mean processing time of computer 2? Yes, we can. The true statement was that it was less, right? So can we conclude that it's less? Yes, we can. All right, number 8. Basically this is, whoa, the same kind of thing here, but we've got our lifetime of light bulbs in hours in a table. So again on this one, because we need the mean and we need the standard deviation, we're just going to use our calculator and do list 1 and list 2 and find those calculations. So you two in the front want to do list 1 and you two in the back want to do list 2. It says a purchasing manager for a large university is investigating which brand of LCD projectors to purchase to equip a smart classroom. Of major concern is the longevity of the light bulbs used in the projectors. The purchasing managers have narrowed down the choices of projector to 2 brands, In Focus or Proxima, and wishes to determine if there is any difference between the 2 brands and the mean lifetimes of the bulbs. The purchasing manager obtained 8 projectors of each brand. So we know we have 8 there. The number of hours the bulbs lasted in each of the 8 machines are given in my table. Assume the 2 populations of lifetimes are normally distributed and that the populations variances are equal. Can we conclude at the 0.01 level of significance that there is a difference in the mean lifetimes? So in here again, we're going to say mean 1 minus mean 2 mean 1 minus mean 2. And the question wants to know, is there a difference? When it asks, is there a difference? My null is going to say, it's equal to 0. My alternative one, not equal to 0. So is there a difference? I'm going to subtract. If there's no difference, it would be equal to 0. If there is a difference, not equal to 0. So hopefully you've got some of that typed in there. My mean of my first set of data. So the mean of this set of data here. Did you guys get that into list 1?
Oh.
And then, yep, stat, calculate your one variable statistics.
Which one did
The X bar, the mean.
43.375.
375. My standard deviation, the S1 of that list of data.
80.096.
Yep. And the N, how many numbers did we have on that list? We had 8, right?
Yeah.
On my second list of data, so on my bottom list of data, the mean of the second list was
775.375.
775.375. My standard deviation for my second set of data is 101.410, and my number of values was 8 again, right? All right, degree of freedom, I'm going to do that right away. For my degree of freedom, we did N1 plus N2 minus 2. So in this case, we have 8 plus 8 minus 2. 16 minus 2 gives us 14 degree of freedom. So over here, what type of test? We're doing the t-test with the degree of freedom of 14. I'm not leaving myself much writing room. I have to do my first formula. My first formula for my SP. We did N1 minus 1. So 8 minus 1 times the standard deviation squared. So 80.096 squared plus N2 minus 1. So again, we have 8 minus 1 times our standard deviation squared, 101.410. You can almost read my 4. That was squared. That is all over the degree of freedom, which is your 14. I'm just going to put DF there for the degree of freedom. So if we could calculate that SP value and round that to 3 decimal places, what are we coming up with? 8,349.679. We used that when we did the second part of our formula. The second part of our formula, we did x bar of 1 minus x bar of 2 divided by the square root of that SP value times 1 over N1 plus 1 over N2. So our X bar from 1, 843.375, minus the X bar from 2, 775.375, over the square root of that answer we got there, 8349.679 times 1 over N1, which is 8, plus 1 over N2, which is also 8.
One point four eight eight.
1.488. All right. We are going to find the p-value on this one. So we are going to do the p of t is greater than 1.488 with a degree of freedom of 14. The p-value is the percentage that's in that section. Again, I'm going to draw my little table here because we were doing a two-tailed test. So when you do P of t is greater than 1.488 with a degree of freedom of 14, you get we get 0.079. Now that's the percent that's in this section. We're doing a two-tailed test. So that means the percent that's in this other section is also 0.079. So in order to find our total percentage, we either have to add those together or multiply by 2 since they're the same number, right? Kind of remember doing that last week when we did the t-test and we had a two-tailed test? When we do the p-value, if I'm doing the two-tailed test, I end up multiplying it by 2 since I'm doing both ends. The percent on this end is 7.9, the percent on this end is 7.9, so if we add them together, we get
Use it add.
yep, or multiply by 2, either way, it's the same thing, right?
0.158.
0.158. So that means we have a 15.8% confidence that we have the thing correct. We want to test it at a 0.01 level. So 0.158. Is that greater than or less than 0.01? It is greater than. And if my p-value is greater than my level of significance, we are going to do what? Accept the null. We're going to say this is our true statement, then that one is not true. We're saying it is equal, right? So, can we conclude that there is a difference in the mean lifetimes? Can we say there's a difference? No, we're saying it's equal. There is not a difference. I didn't leave space for the no, but on the bottom one, you're going to circle no. We're saying they're the same. They're not different. Okay? Number 9, same kind of thing. Good, they gave us all the data. We don't have to figure it out. So, the University Data Center has 2 main computers. The center wants to examine whether computer 1 is receiving tasks which require comparable processing times to those of computer 2. A random sample of 15 processing times, N1 is 15, from computer 1 showed a mean of 58 seconds, so X bar 1 is 58 seconds, with a standard deviation of 20 seconds, so S1 is 20. While a random sample of 10 processing times from computer 2, so N2 is 10, showed a mean of 53 seconds with a standard deviation of 16 seconds. So X bar 2 is 53 seconds, standard deviation 2 was 16 seconds. Assume the populations of processing times are normally distributed for each of the 2 computers and that the variances are equal. Can we conclude at a 0.5 level of significance that the mean processing time of computer 1 is greater than the mean processing time of computer 2? So we want the mean of 1 to be greater than the mean of 2. Of course, they're going to rearrange those. The greater than would be which one, the null or the alternative hypothesis? The alternative. It doesn't have an equal sign in it, right? So we're going to rearrange this and say the mean of 1 minus the mean of 2 is greater than 0, which means this one is the mean of 1 minus the mean of 2 is less than or equal to 0, right? The null always has the equal to in it, which means on this one we're doing a right-tailed test. As long as I'm figuring it out, I'm doing the greater. All right, the type of test statistic, we know that it's a t-test. We have to find the degree of freedom. How are we going to find the degree of freedom? 15 plus 10 minus 2. N1 plus N2 minus 2. 25 minus 2 is 23. Oops, degree of freedom of 23. All right. We then have to find the value of our test statistic, but first of all, before we can do that, we have to find SP. SP. I'm going to take N1 minus 1 times the standard deviation squared. So 15 minus 1 times 20 squared plus N2 minus 1 times the standard deviation squared. So 10 minus 1 times 16 squared, all over the degree of freedom, that 23 that we had. To 3 decimal places we get 652. 343.652. Now we can find the value of our test statistic by taking the mean of the first minus the mean of the second over the square root of that SP value times 1 over N1 plus 1 over N2. So the mean of the first, 58, minus the mean of the second, 53 over the square root of our lovely number we got there. 343.652 times 1 over n1, which was 15, plus 1 over n2, which is 10. So 58 minus 53, subtracting my means over the square root of SP, which is our number we found here, times 1 over n1 plus 1 over n2. So 1/15 plus 1/10. And again, we're rounding to 3 decimal places. Yep. 0.661 is what you should be coming up with. We are doing the critical value. We are doing a right-tailed test. So on our critical value, we're going to do T sub. Since it's just a one-tailed test, we use that number, 0.05 with a degree of freedom of 23. Since I'm going to the right, I should get my positive number. If I was going to the left, I'd have to use the negative, but we're going to get the positive. So when you punch that in, your critical value is going to be 1.714. So 1.714 is my cutoff between the two sections. The greater than section is your alternative hypothesis. That's your H1, which means the less than or equal to on the left side is your null. Does your test value, the 0.661, fall on the left or on the right of that critical value? It falls on the left. We know that the 0.661 is in that section. That means that my null statement is the one that's true. That means my alternative one is not true. So, can we conclude that the mean processing times of computer 1 is greater than computer 2? Can we say computer 1 is greater than computer 2? I think I heard somebody whisper.
Oh, no, you can't.
No, we can't. That is not true. We're saying that's the not true statement, the one with the greater than. So, no, we can't conclude that. It's not true. All right, the next hypothesis test is for the difference in population proportions. So, population proportions, that's when we had all those lovely fractions. It says, 2 popular drugs used for the treatment of whatever that is, an eczema. A random sample of 475 depressed individuals is selected and treated with Recithin or something, and 242 find relief from their depression. In a sample of 465 depressed individuals that's independently selected from the first sample and is treated with eczema or whatever that is, 205 find relief. Can we conclude at a 0.1 level of significance that P1 of all depressed individuals that find relief from depression is greater than P2? So P1 is greater than P2. Again, this is just like the other ones when we're comparing it to 0. Whenever we do the difference, we're going to compare it to 0. So P1 minus P2 would be greater than 0, would be my alternative hypothesis. P1 minus P2 is less than or equal to 0, then is my null. My null always has the equal in it. So on this one, when we're doing our test, we're doing a greater than, so we're doing that right-tailed test. The alternative is the greater than. The less than or equal to is our no. So, this time when we do our formula, we are going to do p hat 1 minus p hat 2. Again, we're minusing this 0 part over there, so we're not going to worry about the 0 because we know the difference is 0. But if you look in the book, they'll have that in there. Over the square root of p hat times q hat. I didn't put my 1s and my 2s in there. I gotta look to see what number I stuck there. Oh, I got a formula for that. Find p hat and q hat. Okay. Times 1 over n1 plus 1 over n2. All right. So, p hat 1 is going to be the proportion from sample 1. On sample 1, 242 found relief out of the 475, right? 242 out of 475. So N1 in this case is going to be 475. And I don't know why I wrote that other number down. I don't need it. On the second one, P hat for 2. On my second survey, 205 found relief out of 465. 205 out of 465. And 2 is the 465, right? All right. So, in order to find the p-value, just the plain p hat, we are going to do, that's why I wrote the x, the means. We are going to take, I wrote this weird. Look at this. Oh, the numerators, that's what that is for. Okay. We are going to take the numerators from each of these fractions and add them together, and then the denominators from each of those fractions and add them together. So I'm going to take my 242 plus my 205 over my 475 plus my 465. So take the numerators of each of your fractions, add them together, and then the denominators from each of your fractions, add them together. And so, when we calculate p hat, if you take 242 plus 205 over 475 plus 465, you get 0. What? Make sure and you do it on the calculator. You're doing it on the Alex calculator, right? Mm-hmm. Yeah, so then you're going to have this on top and then highlight it and divide it by the bottom, right? The whole thing has to be on the bottom. Let's see what we got punched in there. 242 plus 205. Then highlight that whole thing, divided by 475 plus 465. Yep, that's the right number. 0.4755. Rounding that off anyway. All right. So, that means for Q hat, we are going to do 1 minus the P hat, 0.4755. So if you do 1 minus that value,
Like 5, 2, 0.5.
what was that?
5245.
245. Okay? So now we can go to our formula. We're going to do p hat 1 minus p hat 2. So 242 over 475 minus 205 over 465. And that's going to be over the square root of 0.4755 times 0.5245 times 1 over n1, which was 475, plus 1 over n2, which is 465. If I smush all of that in there. Again, all that has to go underneath the square root when you get that punched in. I forgot to do the type of test statistic. This is a z-test that we're doing when we do the proportion problems. So now we get to punch that crazy thing into our calculator. Oop. Click to the box first, yep. 242 over 475. Minus 205 over 465. Highlight that whole thing. Divided by square root. And then our two numbers we got, 0.4755 times 0.5245. And then in parentheses right behind that, we're going to have our 1 over 475 plus our 1 over 465. Parenthesis, 1 over the 475, which was our N1, right behind there, plus, whoops, make sure you get right behind the line. Here we go, plus 1 over 465. And then close the parenthesis on that, and hit equal. So we get what for the value of our test statistic?
2.106.
2.106, okay? So, we're doing a z-test. Again, on the z-test, it's p of z is less than, right? On your calculator, we want to do greater than, so since we're doing a greater than instead of a less than, we're going to do 1 minus that value. 1 minus p of z is less than our 2.106. Zero point 018. Okay, this is the percentage, the p-value. We're comparing it to the level of significance. And so if I have 0.018 and I'm comparing it to 0.01, is 0.018 greater than or less than 0.01? It is greater than. And if my test value is greater than my level of significance, what am I going to do? Accept the null. Accept the null. That means this is my true statement. This one is, whoops, this one down here is the one that is not true. So the true statement is it's less than or equal to. Can we conclude that the proportion of depressed individuals taking whatever that first medicine is who find relief is greater than the ones taking the second medicine? Can we conclude that it's greater? No, the greater than was the not true statement, right? So no, we cannot conclude it's greater than. That was not true. Doesn't want to stay there. Keeps moving. All right. Number 11. The General Social Survey is an annual survey given to about 1,500 U.S. adults selected at random. Each year the survey contains several questions meant to probe respondents' views of employment. A recent survey contained the question, how important to your life is having a fulfilling job? Of the 242 college graduates surveyed, 109 chose very important. Of the 133 people surveyed with the highest level of education of high school or less, 78 chose very important. Based on this data, can we conclude at a 0.5 level of significance that there is a difference between P1, which is the college graduates, and PT, which is or P2, which is those whose highest level of education was high school? So, is there a difference? P1 being equal to P2 or P1 being not equal to P2, but of course they're going to rearrange those and set them equal to 0, right? So P1 minus P2 either equals 0 or P1 minus P2 being not equal to 0. They are different, right? So again, this one's going to be one of those two-tailed tests because it's an equal and a not equal. So we had to start off with our p-hats. P-hat 1. P-hat 1. From those that were college graduates, 109 chose very important out of the 242 that was surveyed. 109 out of 242, which means N1 is my 242. For my second group surveyed, those that had high school education, 78 out of 133. So 78 out of 133 was my P hat 2. N2 is my 133. So then we had to find just the plain P hat, not P1 or P2. The plain P hat value, we added the numerators together, added the denominators together, and figured out what our answer was. So my numerators, 109 plus 78. My denominators, 242 plus 133.
And 4987.
0.4987. My Q hat is 1 minus that value. So 1 minus 0.4987 would give me 0.5013. Okay, once we have all our data, we can now plug them into our formula. So on the top of our formula, we're doing P hat minus, or P1 hat minus P2 hat. So those two fractions we have. 109 over 242 minus 78 over 133. On the bottom of our fraction, we have the p hat times the, or the p times the q, p hat times q hat. So these two decimal numbers we got here, 0.4987, 0.4987 times 0.5013. And then in parentheses, 1 over n1 and 1 over n2. So 1 over 242 plus 1 over 133. I forgot to put my test statistic in there again. Z-test when we're doing proportions. Negative 2.521 it rounds off to. Okay. We are going to do the critical value. Again, we're doing a two-tailed test. So on this critical value, we're going to divide it by 2 since we have that two-tailed test. So we're going to use Z sub what number? 0.025. Right? We have 0.025 on this end, 0.025 on that end as far as our percentages. So if we do that, our critical values. $1.960 and negative 1.960 since we're doing that two-tailed test. So 1.960 would be the value here, negative 1.960 would be the value here. Our null would be in the middle. Our alternative ones would be if I'm on the two ends. So I'm going to look at my test value and decide where would my test value fall. Is it way to the left? Is it in the middle of those two numbers, or is it on the right side? It's on the left. Negative 2.521 is less than negative 9.60. So since it's on the left, we're in the H1 section. My alternative hypothesis is my true one, which means my null is not true. So the question says, can we conclude that there is a difference? Yes, we can. They're not equal, which means there is a difference. That is my true statement. Yes, we can conclude there is a difference. They're not equal. Number 12, same kind of thing. Got the whole thing? No, there we go. Large companies typically collect volumes of data before designing a product, not only to gain information as to whether the product should be released, but also to pinpoint which markets would be best targets for the product. Several months ago, I was interviewed by such a company while shopping at a mall. I was asked about my exercise habits and whether or not I'd be interested in buying a video/DVD designed to teach stretching exercises. I fall into the male 18 to 35-year-old category. I guess that, like me, many males in the category would not be interested in a stretching video. My friend Holly falls in the female older than 35 category, and I was thinking she might like the stretching video. After being interviewed, I looked at the interviewer's results. Of the 96 people in my market category who have been interviewed, 20 said they would buy the product. Of the 107 people in Holly's market category, 27 said they would buy it. Assuming that these data came from independent random samples, can we conclude at the 0.1 level of significance that the proportion from P1, which is all the mall shoppers in the male category who would buy the product, is less than P2, which is the ones in Holly's category? So we want to decide, can P1 be less than P2 is what the question says. The less than goes in for the alternative hypothesis, right? Of course, we're going to rearrange it so it's 0. So P1 minus P2 is less than 0 is my alternative hypothesis. P1 minus P2 is greater than or equal to 0, then it's my null. So we're doing a left-tailed test. We're checking less than for my alternative, which means my null would be over on this side, the greater than or equal to, right? So again, we have to have all our proportions and fractions and all of that fun stuff. My proportion for the first sample, for the males, what was my proportion for the males? 20 out of 96, right? Which means N1 is 96. For my females, which is my proportion for 2, (27 out of 107), which means my N2 is my 107. So now if I'm just doing my plain P hat, my plain P hat that doesn't have a subscript is going to be my numerators added together over my denominators added together. So I'm going to have 20 plus 27 over 96 plus 107. Point 2.
3, 1?
No.
6? I don't know.
2, 5. 2, 3 is what we should be getting, right? Wait a minute. Nope, I lied. I'm looking at the wrong number. You were probably right, and I'm telling you you're not. What did you get again?
0.236?
1, 5?
1, 5? Okay.
You got 1, 5 there? Okay. 0.2315. I was reading the wrong number. All right. P hat is 0.2315, which means Q hat is 1 minus that number. So if we do 1 minus 0.2315, we get 0.7685. Now that we have all those numbers, we can plug them into our formula to get our test value. So in the numerator of our test value, we are going to subtract our P1 and our P2, right? So 20 over 96 minus 27 over 107. On the bottom of that fraction, that's where I have that big long square root. I'm going to take my p-value, 0.2315, times my q-value, 0.7685, and then in parentheses, 1 over N1, which is how many I had in sample 1, plus 1 over N2, and I had 107 in my sample 2. So 1 over 96 plus 1 over 107. I forgot to write down that I was doing the z-test again. Since I'm doing proportions, I'm doing the z-test.
-0.7421.
So we'll round that off to negative 7.4, or negative 0.742, right? 3 decimal places. Negative 0.742. This one we are finding the p-value. Since we're doing the p-value on our calculator does p of z is less than. We are doing a left-tailed test, so we're just going to put p of z is less than our negative 0.742. We don't need the 1 minus since it's not a right-tailed test, it's a left-tailed test. 0.229. We are comparing that percent to our critical value, which is 0.1. So 0.229 compared to 0.1 is greater than. And if my test value is greater than my critical value, I am going to accept the null. So this one's my true statement. This one would be not true. Can we conclude that the proportion of all mall shoppers in my market category who would buy the product is less than the proportion? Can we conclude that it's less? No, we're going to say that it's greater than or equal to. That's the true statement. The true statement was greater than or equal to, so we can't say it's less. No, we cannot conclude that it's less. Number 13, now we're doing the population variances. That's the one where we calculated the F statistic and we used the variance squared of 1 over the variance squared of 2 at the very end of homework 18. So, on this one, an examination in psychology has been taken by both psychology majors and by some students from other majors. It is widely believed that the scores for both groups are normally distributed. A random sample of 29 examinations completed by psychology majors in an independent random sample of 23 examinations completed by students from other majors are selected. Among the sample students, the psychology major scored a mean of 526.6 with the important number, the variance, of 10,140.49. And the students from the other major scored a mean of 501.5 with a variance of 15,276.96. Can we conclude at a 0.1 level of significance that the population variance of scores of a psychology major is less than the population variance of scores of other majors? So on this one, when they do these, it's going to look kind of weird. they're going to have the population variance of 1 divided by the population variance of 2. If I have the same number over itself, I'm comparing it to 1 instead of comparing it to 0 like we did with the differences. And so in this case, we want to know, can we conclude that that is less? If I'm just doing the less, that's my alternative hypothesis. So is my variance for 1 compared to my variance for 2 less than 1? I could draw. This one then would be greater than or equal to. So here I'm doing a one-tailed test. I am doing less than, so here would be where my alternative one is. There's where my null is. The type of test statistic I'm doing is my F test. And on my F test, I have to have my degree of freedom in my numerator and my denominator. My degree of freedom in my numerator is N1 minus 1. So 29 minus 1 would be 28. My degree of freedom in my denominator is N2 minus 1. N2 was 23. 23 minus 1 is 22. So I'm going to have my degree of freedom in my numerator as 28. My degree of freedom in my denominator is 22. I'm going to just find the value of my test statistic by dividing out my 2 sample variances. So I'm going to take the 10,140.49 divided by my 15,276.96, and that's going to give me the value of my test statistic. So that one's a lot easier to calculate than most of them have been. So when you divide 10,140.49 divided by 15,276.96, what do we get? 0.664 then, okay? We're doing the p-value. On the Alex calculator, when you do the p of f, is it a greater than or a less than? It is a greater than. We're checking less than, which means we have to do 1 minus the p of f is greater than 0.664, because we're going the opposite way of what the calculator does, right? So if you do 1 minus p of f is greater than 0.664, whoops, I forgot my degrees of freedom. Degree of freedom in my numerator, 28. Degree of freedom in my denominator, 22. I tried to forget those last time too. 0.152. 0.152. We're testing the p-value, so we're comparing it to the level of significance. Our level of significance that we are checking is 0.1. So 0.152 compared to 0.1 would be greater than. If it's a greater than, we are going to accept the null. This is my true statement. This is not true. So, can we conclude that the variance is less than? Can we say this is less than? No, because that was the not true statement, right? No. That was the not true statement. We just got 2 more here we're going to go through quick. All right, these ones don't take a whole lot of time anyway. So, again, on this one, actuaries use various parameters when evaluating the cost of life insurance. The variance lifespans of population is one of the parameters used for the evaluation. Each year, the actuaries at a particular insurance company randomly sample 20 people who died during the year, with the samples chosen independently from year to year, which means here N1 is going to be 20, over here N2 is also going to be 20, because they do 20 of them each year, right? The first row gives the sample mean, the second one gives the sample variance. Assume the lifespans are approximately normally distributed. Can we conclude at a 0.5 level of significance that the lifespan for the current year differs from the lifespan for the last year? So in this case, when we do differs, our null is going to be equal, our alternative one not equal. So we're going to have that weird fraction again. My variance of 1 over my variance of 2 is either going to equal 1 or not equal 1. The variance of the first divided by the variance of the second either equals 1, or the variance of the first divided by the variance of the second does not equal 1. The type of test we're going to do, an F test, and then we've got to do our degree of freedom. So my degree of freedom in my numerator, 20 minus 1, which is 19. My degree of freedom in my denominator is also 20 minus 1, because each year we did 20, so it's 19. So degree of freedom in my numerator, 19. Degree of freedom in my denominator, 19. I'm now going to find the value of my test statistic. To find the value of my test statistic, I'm going to divide my variances. So I'm going to take 59.29 divided by 136.89. .433. Okay? We are doing a two-tailed test on this one since we're doing an equal and a not equal, right? So, if we do, I'm trying to remember if I get the same number when I do both ends. No, I think I have to do minus. Because this one we are doing F is greater than. Let's just try it. I'm curious now. If you do P of F is greater than 0.433, whoops, I got to put my degree of freedom on there. Degree of freedom in my numerator being 19 and degree of freedom in my denominator being 19. What do you get for your number? Nope, that wasn't the right number. Okay, I do have to do the minus in there. I have to do the 1 minus in there since I'm doing the greater. I was thinking maybe I'd get the same number, but I don't. So do 1 minus P of F is greater than 0.433 with my degree of freedom of 19 in my denominator and my numerator. All right, so what I'm really getting there, 0.038, is the percent in the left side since I did 1 minus this value. The percent in the right side should be the same number. Whoops, 0.038. The percent in the right side should be the same number. I was hoping we could just do the first one, but we have to do the left side, so we have to do 1 minus. Since those 2% are the same, I can either add them together or multiply by 2 to find my p-value. So 0.038 plus another 0.038 would give me 0.076. I am then going to compare that to my level of significance. So 0.076 compared to 0.05. Is that less than or is that greater than? It is greater than. And if that's a greater than, we are going to accept the null. So this is the true statement. This one is not true then. So the bottom that you can't see on mine says, can we conclude that there is a difference? Can we conclude there is a difference? No, because the not true is the not equal, right? The true statement is that they are equal. So no, there is no difference. And quickly, although we're a little over time, let's do the last one so we have it done. All right. The psychologists studied the alcohol consumption patterns of two people in two age groups. One group consisted of people aged 21 to 35, the other people 36 to 50. The psychologist interviewed an independent sample from each group. She assigned a score from 0 to 100 to each individual. 0 meant no alcohol consumption, and the results are summarized below. So here, 27 people were surveyed. Here, 20 were surveyed. So, first of all, we want to know, assuming that these are approximately normally distributed, assume for the same scores of all people, can we conclude at the 0.5 level of significance that the variance for people from 21 to 35 is greater than the variance 36 to 50? So my greater than is going to go for my alternative hypothesis. So my variance from my first divided by my variance of my second is greater than 1, or for my null, the variance of the first divided by the variance of the second then would be less than or equal to 1. Which means we are doing a right-tailed test. Our type of test statistic, we're doing the F test. And we have to find the degree of freedom in the numerator and the degree of freedom in the denominator. So my degree of freedom in my numerator, 27 minus 1 would be 26. My degree of freedom in my denominator, 20 minus 1, which would be 19. We need to find the value of our test statistic. And so we're just going to take our variance from our first divided by our variance of our second. 225 divided by 118.81. 1.894. This time we're doing the critical value instead of the p-value. For the critical value, we use the subscript one. So we're going to use F sub. And since we're just doing a one-tailed test, we use the number that's there. If it was a two-tailed test, we'd have to divide that by 2. But in this case, it's a one-tailed test. So 0.05, degree of freedom in the numerator of 26, degree of freedom in the denominator of 19. .098. So that means 2.098 is our critical value, divides our normal curve in two parts. We want to check where that test value falls. Again, the greater than is my H1, the less than or equal to is my H0, my null. So, does 1.894 fall or be less than or greater than my 2.098? My 1.894, is that less or greater than the 2.098? It's less than. It's going to be over here on this side then, right? 1.894 is smaller than 2.098. That means that the null, the less than part is true. This is my true. This one then would be not true. Again, I cut off the bottom, but you have your paper. Can we conclude that the variance for the 21 to 35-year-olds is greater than the variance from the 36 to 50-year-olds? Can we conclude it's greater? No, because that's the not true section, right? The greater was not true, so no is the answer to the bottom question that you can't see. All right, we did